Black holes are known for being the most terrifying objects in the universe, regions of space with such immense gravity that nothing can escape their grasp. The boundary of this region is called the event horizon, and it is also the point of no return. But what if the event horizon isn't an end, but a beginning? What if black holes aren't cosmic monsters, but gateways to other realities? In this video, we will explore the possibility that the inner side of a black hole's event horizon could be a doorway to another universe, or perhaps even our own universe at a different point in time. Before we start, make sure to subscribe so you won't miss out on future videos about the secrets of the universe. Part 1. The basics of black holes. Let's start by explaining what a black hole is. When a star many times larger than our sun runs out of fuel, it collapses under the force of its own gravity. If the star is massive enough, this collapse continues until gravity overwhelms all other forces of nature, including the electromagnetic force and the strong and weak nuclear forces. At this point, the collapsed star has become so dense that not even light can escape its gravitational pull. And so, a black hole is born? The boundary of this region from which nothing can escape is called the event horizon. The size of the event horizon is determined by the mass of the black hole. The more massive the black hole, the larger the radius of the event horizon. Once something crosses the event horizon, it cannot come back out. Not only would this require the object to travel faster than the speed of light, which is impossible, but it would also take an infinite amount of time for the object to reach the distant observer. This is because the closer you get to a black hole, the slower time passes relative to an observer far away from the black hole. As a result, an object falling into a black hole appears to slow down dramatically as it approaches the event horizon and eventually seems to freeze completely. Part 2. Einstein's relativity. Einstein's theory of general relativity describes how gravity works. Massive objects warp the fabric of spacetime around them. The more massive an object, the greater the curvature of spacetime around it. When a black hole is formed, the fabric of spacetime curves dramatically around it. This means that if you were to fall into a black hole, you would experience a tremendous amount of gravitational force. This force is known as spaghettification due to the fact that it would stretch your body into a thin noodle shape. At the center of a black hole is a region known as the singularity. It is a point of infinite density where the laws of physics as we know them break down. Nothing can escape the singularity, not even light. For an object approaching a black hole, the gravitational force increases dramatically as it gets closer and closer to the singularity. However, once it crosses the event horizon, the gravitational force remains constant. This is because the event horizon acts as a kind of buffer, preventing the gravitational force from increasing any further. Therefore, if you were to fall into a black hole, you wouldn't be crushed by the intense gravity, but instead you would experience a constant gravitational force equal to the force experienced at the event horizon. It's important to note that while this may seem like a relief, it wouldn't actually save you. That's because the gravitational force at the event horizon of a typical black hole would be thousands, if not millions, times greater than the Earth's gravity. You'd be utterly crushed into a pancake. In addition, the intense energy and radiation near a black hole would tear apart even the atoms that make up your body. So, while crossing the event horizon wouldn't immediately cause you to be ripped apart by gravity, it wouldn't keep you alive either. Part 3. The wormhole theory. According to Einstein's theory of general relativity, there is a region just outside the event horizon called the marginally trapped region. This region is characterized by a peculiar property of spacetime known as null convergence. At the edge of the marginally trapped region, parallel rays of light begin to converge. And as they approach the center of the black hole, they come closer and closer together until they reach the event horizon. Here, all light rays coming from the same direction are parallel. If one were to cross the event horizon of a black hole and continue traveling inward, the rays of light would begin to diverge, moving away from each other. This would create a tunnel-like structure connecting the two sides of the event horizon. If this tunnel extended all the way to the singularity, then it would effectively connect the two sides of the event horizon. This is the basic idea behind the wormhole theory of black holes. It suggests that black holes are essentially tunnels or wormholes that connect different regions of space. According to this theory, when an object falls into a black hole, It doesn't disappear, but instead emerges on the other side of the wormhole at a different location in the universe. However, it is important to note that this is just a theory and there is no evidence to support it. In fact, according to Einstein's general relativity, which is the current best theory we have to describe gravity, it's actually impossible for anything to travel through a wormhole because it would require infinite energy. That said, there are some physicists who have proposed modifications to general relativity that allow for the possibility of traversable wormholes. One such modification is the use of negative masses or exotic matter. If a wormhole is created using negative masses, then the required energy could be provided by the negative gravitational potential energy of the mass. Another way to create a traversable wormhole is to use quantum entanglement. By entangling two regions of space, it's possible to create a wormhole-like connection between them. However, these are just theoretical ideas, and there is no evidence that either of these methods is possible in reality. Part 4. The information paradox. One of the main reasons why the wormhole theory of black holes is so appealing is that it provides a solution to the black hole information paradox. This paradox arises because of the apparent conflict between quantum mechanics and Einstein's general relativity. Quantum mechanics tells us that information cannot be destroyed, but general relativity suggests that once something falls into a black hole, it's gone forever. This means that either quantum mechanics or general relativity must be wrong. However, if black holes are actually wormholes, then the information paradox disappears. That's because the information that falls into a black hole is not destroyed, but instead is transported to the other side of the wormhole. But unfortunately, the information paradox is not the only problem with the wormhole theory of black holes. There are other physicists who argue that the wormhole theory is incompatible with another well-established theory in quantum physics known as quantum field theory. They claim that the wormhole theory leads to inconsistencies in the behavior of particles and their interactions. These inconsistencies arise because the wormhole theory requires the introduction of new mathematical structures called junction conditions at the surface of the black hole. These conditions are supposed to describe how the physics of one side of the black hole matches up with the physics of the other side. However, it turns out that these matching conditions cannot be satisfied simultaneously, leading to inconsistencies. As a result, some physicists argue that the wormhole theory of black holes is simply not a viable option. Ending. So what do we really know about what happens inside a black hole? The answer is that we don't know much. We go in, observe what happens inside a black hole directly. Since no light or matter can escape its event horizon, any object that crosses the event horizon of a black hole is lost forever. We can only observe the effects of a black hole on things outside of it. While scientists have developed various theories about what might happen inside a black hole, these are just that, theories. Without the ability to observe what happens inside a black hole, we can only speculate. Some physicists believe that the inner side of a black hole's event horizon might be a doorway to another universe, or perhaps even our own universe at a different point in time. Others argue that the event horizon is a one-way membrane that allows information to pass through in only one direction. According to this view, information can only move from the outside of the event horizon to the inside, but not the other way around. This means that while an object may appear to disappear behind a black hole, its information is actually being preserved. The discrepancy arises because of the way information is processed on the two sides of the event horizon. On the outside, information is processed in real time, while on the inside, information is processed in a scrambled and delayed manner. This results in the apparent disappearance of the object behind the black hole. However, the information about the object is still present on the inside of the event horizon, albeit in a highly distorted form. What do you think? Do black holes destroy everything that enters them, or do they transport it somewhere else? Let us know in the comments below. Do you even forget to like the video and subscribe for more videos about the amazing discoveries made by scientists who are exploring the unknown? And thank you for watching!